Hi everybody, and welcome to the introductory video for Lab 1, Review of Rocks and Minerals for Geology 109, Evolution of the Earth for UW Oshkosh Spring 2021. Since we are only going to be meeting in person for labs a handful of times this semester, I'll be doing these kind of introductory videos to the labs, whether we meet in person or whether the lab is entirely online. So it's important that you watch this video before you come to lab, maybe watch it more than once, so that way when you do come to lab, you can get started right away and we can keep practicing social distance and move you in and out of the lab as quickly as possible. So for this first week, we're going to be doing a review of minerals and rocks that you should have seen in your previous geology course, whether that was physical geology, environmental geology, or some equivalent. Now, there's different types of groups of rocks, igneous, metamorphic, and sedimentary, that we'll be covering in this course. But for this week, we're going to be focusing on minerals, igneous rocks, and metamorphic rocks. We deal with sedimentary rocks more than the others in this course, so we will dedicate next week's lab to sediments and sedimentary rocks in completion. So for now, let's get started on our review of minerals and igneous and metamorphic rocks. Rocks and minerals are not exactly the same thing. Rocks are composed of minerals, the same way where if you were going to build a house, you would go to a hardware store and buy the supplies to make a house. Minerals are the ingredients that make up rocks. So rocks are aggregates of different types of minerals. So how do we identify or define something as a mineral? A mineral has to meet four very specific criteria. First, it has to be naturally occurring. Has to exist in nature. Sure, many of these minerals we can make in a laboratory setting, and that's cool, but that doesn't count as being a true mineral in the natural sense of the term. Second, it has to be an inorganic substance. The word organic is kicked around a lot these days. What we're referring to in this case with inorganic is it does not come from a living source. So organic meaning of derived from a living thing. If you were to walk down a beach and pick up a seashell, that is a shell that was made by a marine organism. It was made by an animal, and that's how it was put together. An animal ingested certain materials in its food source and then secreted or grew this shell, and if it's a common shell, it would be made of something called calcium carbonate. Now, we have a mineral that's made of calcium carbonate that we call calcite. So would that be a calcite shell? Well, technically, no. It's made of the same thing, but a true mineral has to grow on its own under the environmental conditions for which it's forming, not biological though. So if that shell were to dissolve and then re-precipitate out through evaporation, then sure, then we'd call it a mineral. But if it was made by an organism, we don't call it a mineral. A mineral also has to have an orderly atomic arrangement, meaning that the atoms that make up this structure have to be in a three-dimensional crystal lattice. So like a solid, okay? It can't be, once you melt it down, it doesn't count anymore. It has to regrow into a three-dimensional crystalline structure. And finally, it has to have a definite chemical composition. So let me show you an example. Okay, so let's say we were looking at the mineral halite, which is NaCl. That is halites. We'll call it halite. This is table salt, by the way. Common table salt is sodium chloride, or the mineral name is halite. If you have one sodium ion and one chlorine ion, you have halite. Well, what if we changed it up a little bit? Let's say instead of a sodium, we used hydrogen. So HCl. This is not sodium chloride. This is hydrochloric acid. So this is something that's important that your body has in it. This will kill you in strong enough concentrations. Another example, here's a chemical formula you all should know, which would be this H2O, right? Basic water. Well, that's one hydrogen, or I'm sorry, two hydrogens to one oxygen, but what if we just added one more oxygen? So what if we did H2O2? Now we have hydrogen peroxide. So again, water is necessary for life. Hydrogen peroxide, again, is toxic. So we can't play around with the chemical formulas. If the mineral has a certain chemical composition, then that is its chemical composition. So what is a mineral? It's a naturally occurring inorganic substance with an ordered atomic arrangement and a definite chemical composition. It has to have all four of those criteria before we can call a substance a mineral. Well, now that we know how to identify a substance as a mineral, how do we tell one mineral from another? In order to do this, we have to apply the same type of skills that any scientist or even your doctor might use. If you went into the doctor's office and had a couple of symptoms of like a runny nose and a sore throat, they're going to run a bunch of tests and figure out what virus or illness you have. What they're not going to do is look at one symptom and diagnose you with some disease. They look at a variety of things. That's a differential diagnosis. As such, when we identify minerals from one, or separate them from one kind or another, we're going to use a number of physical properties of that mineral to get an idea what it is. Because the physical properties that a mineral possesses is a reflection of its chemical composition, its crystalline structure, and how it formed. So one of the properties that we use is simply color. What color is the mineral that you're looking at? And as you can see just from this image, there's a wide variety of different shades and colors. Not to mention, most minerals can be a wide variety of different colors. So if you've ever seen the purple gemstone amethyst, that's just quartz. If you look at citrine, which is like an orange mineral, that's also just quartz. Or rose quartz, it's just quartz. A lot of minerals can have a wide variety of different colors because the colors are telling you something about an impurity in the chemical composition sometimes. What we're going to do for this course is keep our minerals to light colored or dark colored because that's where we're starting to see a major reflection in heavy metallic elements in that mineral versus more silica and oxygen in the mineral. So when you look at the minerals in lab, when it's asking you about color, you're going to separate them simply into light colored or dark colored. What you don't want to do is get in the bad habit of looking at a mineral and saying, oh, I know what that one is, it's the pink one. Because a lot of them can be pink or green or blue or clear or brown, right? So you want to just kind of focus on, is it light colored or dark colored, and mark that down as evidence, but that's not going to completely diagnose the mineral. We also use the physical property of luster to diagnose a mineral. Now again, luster is simply the way in which a mineral sample reflects light. So how does it appear in light? And as you can see, we have greasy, pearly, earthy, metallic, non-metallic. There's all these different wide varieties of descriptors we can use. Again, for this class, we're going to keep it kind of simple. I want you to pay attention to whether your minerals have a metallic or a non-metallic luster, because sometimes it can get a little confusing when somebody's talking about earthy, pearly, greasy. Some of those are personal descriptors. But non-metallic versus metallic is pretty simple. Either it looks like it's made of metal or it doesn't. And so that's going to tell you a lot about that mineral's composition right there. I want to go back to color for one moment, because when you're looking at a mineral sample and you're looking at what color it is, you're looking at the whole or a generally whole color for that mineral. However, we know that some materials can change properties when they undergo certain basic chemical reactions, like oxidation. If you're not familiar with the word oxidation, think about what your car does after repeated winters in Wisconsin. It starts to rust. That's the metal in your car oxidizing, and it changes. So what if we took a mineral and we oxidized a very small part of it? It might be the same color as the hand sample. It might be totally different. To do this, we take a small unglazed porcelain tile like you see in the image here, and we take our mineral sample and we scratch it against it. And sometimes it leaves a color that is either similar or different than the mineral sample itself. So for example, the mineral hematite, which is a metallic mineral, it looks silvery. When you scratch it on the streak plate, it leaves a reddish brown streak because hematite is iron oxide. So when you're scratching it, you are causing it to rust instantly. Think of it as when you look at color, you're looking at the bulk color of the hand sample. When you're looking at the streak color on the little slide plate, you're looking at the powdered color of this mineral with lots and lots of surface area, so it chemically reacts very quickly. Now, sometimes minerals don't leave a streak. That's fine. That tells you something right there. That's something to note. It doesn't leave a streak. And sometimes the mineral is harder than the streak plate, and it'll scratch the streak plate, so obviously not leaving a streak color. But that too is important information to take note of. And speaking of hardness, we have a scale, a relative scale of hardness that we use to help classify minerals as well. This is the Mohs hardness scale, and it's something that all geologists use when we're looking at minerals. As you can see, talc is considered one of the softest minerals with a relative number of 1, and diamond being a 10, the hardest substance known on Earth, naturally occurring substance known on Earth. And then in between we have corundum, topaz, quartz, and so on. Now, notice then, just to the right of that, you have some common objects and their relative hardnesses. So notice that a steel file is about a 6.5. So a steel file shouldn't be able to scratch quartz, but quartz should be able to scratch a steel file. A penny is about a 3.5. A wire nail is about a 4.5. But notice that a piece of glass, or a glass plane, is about a 5.5. It's just about right there in the middle from 1 to 10 on the Mohs hardness scale. So again, to keep things simple and moving forward in the lab for this week, when you look at minerals and you test their hardnesses, you're going to be given a piece of glass. Now be very careful with that glass. Don't hold it in your hand and press the mineral against it. It'll break, you'll cut yourself, and that's bad. Put the glass plane on the table and scratch the mineral, and you might really have to put in some elbow grease to do that. Really see if you can scratch that glass. If it does scratch the glass, that means that that mineral has a hardness greater than 5.5. If it doesn't scratch the glass, it means it's on that lower end, less than 5.5. Okay, so again, we want to take all of the information we've been looking at so far. You want to take color, streak, hardness, all of these properties, and use those collectively to help diagnose what mineral sample you're looking at. One of our other properties that we use quite a lot is cleavage or fracture. And I'll be honest, this is probably the single most difficult mineral property for people to really grasp, because it involves trying to look at something in 3 dimensions, even though that object may not be perfect. Cleavage is essentially the tendency of a mineral to break smoothly along a couple or one surface. Now, there are some minerals that have no cleavage. We call that fracture then. Some minerals have one direction of cleavage, and some have 2, 3, sometimes 12. Cleavage planes essentially are weak chemical bonds within the 3-dimensional crystal lattice of a mineral. So if you look at the salt grains from your salt shaker, if you take a couple of those and put them in your hand and look at them very closely, you'll see that they make nice little perfect cubes. If you were to go into a salt mine, you'd see that the naturally growing crystals of halite, of which that table salt is derived, form in giant cubes. Now, I have an example of a cube here, and I'm going to use this to demonstrate the cleavage on halite, which, as you can see, is the 3rd mineral down in the examples I've provided here. So a cube has 6 sides, but a cleavage plane isn't a number of sides, it's a number of directions or planes. So for example, in a cube, even though it has 6 sides, we have one plane that would make up the front and back cube from our perspective. That's one direction. And then we have the top and the bottom. That's another direction. And then we have the sides, our 3rd direction. So a cube has 3 cleavage planes at 90 degrees from each other. Now, if you look at the next example down with calcite, notice that they're a little more squished, right? So that would be 3 cleavage planes, or in this case, 2 cleavage planes, not at 90 degrees. Feldspars have 2 cleavage planes that usually are at 90 degrees. And then things like your micas, your muscovites and biotites, they almost like peeling sheets of paper apart. They only have 1 plane of cleavage. So when you look at a mineral, it may have cleavage in one direction and fracture in another, because what you're seeing is a reflection of the chemical structure of that mineral and where the weak bonds are holding those planes together. And then finally, there's some minerals that have, or groups of minerals, I should say, that have some unique properties that, along with other properties, can help you diagnose them. Most minerals that have some type of calcium carbonate component to them, whether it's calcite or dolomite or a number of others, will react with mild hydrochloric acid. So in lab, you'll see little bottles of HCl. Don't worry about the danger of these. I mean, be careful with them. Don't drink them and don't pour them all over your skin. But it's about as strong as lemon juice. But when you drop it on a piece of calcite or dolomite, it will react. It'll fizz and effervesce. Magnetite is a relatively common mineral that, as the name suggests, is magnetic. So you'll see a magnetic attraction with iron filings or a steel nail. And some minerals have a very distinctive taste, like halite. Tastes like table salt because it is table salt. I don't recommend licking all the samples to figure out which one is halite, but that is a property that can hypothetically be tested. Some minerals have a very unique smell to them, like sulfur, for example, smells like rotten eggs. I don't expect to see sulfur in lab this week because I've discovered if you put a sample of sulfur in a box with a bunch of other minerals, they all end up smelling like that. But it does have that property nonetheless. So for the first part of the lab, what you're going to be doing is looking at the 12 minerals that you see listed here. Potassium feldspar, plagioclase feldspar, quartz, muscovite, and biotite, olivine, amphibole, which is a type of hornblende, pyroxene, such as augite, calcite, dolomite, gypsum, kaolinite, halite, hematite, and chlorite. But I'm not going to just be giving you samples and saying, here, figure it out what it is. You'll see that the labs are set up, the table that you'll be filling out for the lab exercise is set up to give you some of those characteristics first. So the first one will be find a mineral with a metallic luster. So which of these has a metallic luster? What is its streak color? What other characteristics do you see? And then there are some tables that are included in the lab reading that give you the composition and the name of minerals with these sets of properties. And so you want to look it up based on the data you've collected and find the name and number that fits best. Okay. Before you get started in that, though, let's take a look at reviewing igneous and metamorphic rocks. As we said before, rocks are aggregates of minerals. You get a whole bunch of minerals and you bring them together and you get a rock. But there's different types of rocks. We have igneous, metamorphic, and sedimentary. Igneous rocks are any rock that is formed from the cooling of magma or lava, or what we just call a melt. These are crystalline interlocking rocks, and they're very, very dense. Usually then when they will break down, they'll erode into sediments, little loose fragments of pre-existing rocks and minerals, and those can accumulate somewhere and get squeezed and form a sedimentary rock. Either an igneous or a sedimentary rock can get buried and squeezed and heated even further and transform into a metamorphic rock. And then if you heat that too much and it melts, we start the whole thing all over again. So any kind of rock can become sedimentary, any kind of rock can become metamorphic, and with enough heat, any rock can melt and be reborn again as an igneous rock. And as I already mentioned, we're going to be focusing on igneous and metamorphics this week, and we'll look at sedimentary next week. So again, igneous rocks are formed from the cooling of a melt, and we're using that in this term as a noun, because we can be looking at magma, which is molten material deep in the earth, or lava, molten material close or at the surface. Okay. So once these cool and we start forming mineral crystals, we can then identify the igneous rock based on two criteria. One, what the texture is, which is another way of saying the size and shape and relationship of those mineral grains with each other, and the composition. The composition of an igneous rock is going to tell us about the composition of the magma or lava from which it formed. The texture tells us more about how and where and the rate at which that igneous rock formed. So we have phaneritic textures, which include large crystals that are a few millimeters in diameter, sometimes really, really big ones we call pegmatites, or aphanitic textures, which is much more fine-grained. You really need a magnifying glass to see any of those little tiny minerals that are interlocked together. Phaneritic rocks cool very slowly, deep in the earth in what we call an intrusive setting. And aphanitic rocks cool relatively quickly in what we call an extrusive setting. So think of it this way. When you have magma or lava, any kind of melt, the longer it takes to cool, the bigger the mineral crystals we're going to see. Now, there are some other types of textures that are important to note. We can also have porphyritic textures. In this case, these are generally finely crystalline or aphanitic rocks, but occasionally have a big, conspicuous, larger phaneritic crystal. Porphyritics then have both kinds of phaneritic and aphanitic textures. So how does that happen? Well, if aphanitic rocks form from magma or lava cooling very quickly, and phaneritic rocks form from magma or lava cooling slowly, what usually happens here is you start out with a magma chamber deep underground and it's cooling slowly. Then you start getting those large crystals forming, otherwise in a mixture of still molten material. And then you extrude that body of magma up to the surface and it cools very, very quickly, trapping those large crystals inside of a matrix of very, very small materials. So the cool thing about porphyritic rocks is that they indicate a two-stage cooling system. We can also have pyroclastic rocks. These are usually things that are ejected from volcanoes or can be welded together from volcanic eruptions. And then we can also have vesicular and cellular types of textures as well. Vesicular is going to be any rock that you can see some holes in it, which is from gas bubbles escaping. And cellular would be, it's pretty much all gas bubbles. This would be something like pumice stone that you might use for exfoliating, is actually a cellular volcanic rock. Now, when we look at composition, we have to keep our texture in mind, but notice on this table, which is from your lab for the week, mineral composition is listed along the top. So our first column, these would be igneous rocks that have the minerals orthoclase, which is potassium feldspar, quartz, and lesser amounts of biotite and hornblende. Now, everything in that column is that type of rock, and we call that a felsic rock. It has feldspar and silica, felsic. Felsic rocks include granite pegmatites, granites, granite porphyries, rhyolites, rhyolite porphyries, rhyolite tuffs. And then we start getting down to pumice and obsidian. Those are glasses, so we really can't make out exactly their mineral composition in some cases. So how do we know which is a granite and which is a rhyolite? Well, if we look then to the left side of this chart, you'll see that if you have a rock, a felsic rock that has orthoclase, quartz, and biotite and hornblende, and it has a coarse-grained phaneritic texture, that's a granite. If it has a fine-grained aphanitic texture and that same composition, it's a rhyolite. And then you can adjust those modifiers accordingly. Now, our next column would be the sodium plagioclase and hornblende group. These don't have as much quartz in them, they don't have as much orthoclase, and they don't have as much biotite, and we call these intermediate rocks. And just like we did before, what's the phaneritic and aphanitic variant? Diorite and andesite, respectively. Andesite is really where you get a mixture of really, really heavy minerals and really, really light minerals, and they melt together, and you produce things, and this is where we get this type of rock in the Andes, which is where the name comes from. Keep in mind, though, that some of these are porphyries, meaning that they have both stages of cooling present. They have big and small crystals. And then finally, we have our calcium plagioclase, olivine, and augite group. These are going to be really heavy rocks. They're going to be very dark in color, and these are what we call mafic. The Ma for magnesium and the Fic for the Latin ferric or ferrous, meaning iron. So these are iron magnesium rich rocks. And these are going to be your gabbros and your basalts, things that make up the seafloor. They're very heavy, they're very dark, very, very dense. So we have our felsic, intermediate, and mafic igneous rocks. And in those three categories, we can have a wide variety of different types of textures, even among similar chemical or mineral compositions. Now, our metamorphic rocks, if you remember, these are rocks that come from a previous type of rock, whether it's an igneous, sedimentary, or even a metamorphic, and the rock is heated and squeezed to the point where it's no longer stable, meaning the minerals that make it up are no longer stable at that temperature and pressure combination. As a result, they transform. You can actually get minerals in metamorphic rocks that only exist in metamorphic rocks because they only form under certain high temperature, high pressure conditions. So while An igneous rock tells you about where that rock formed, and the rate at which it formed. Metamorphic rocks tell you how rocks transform due to deformation. So the main texture that we use for metamorphic rock is foliated or non-foliated. And foliated means layered. Your metamorphic rocks look like they have layers in their fabric. And we also do pay attention, of course, to composition. But some of the foliated textures that you may see in metamorphic rocks include slaty, philitic, schistose, and gneissic. Your slaty foliations are going to be from minerals that are too small to see with the unaided eye, so you need a magnifying glass to see the minerals here. But it's going to have a slate-like texture, so it's going to be very hard layers, but are very, very smooth. And these are usually formed from things like shales or clay stones that become heated and squeezed and flattened out. Now, as that is happening, some of the clay minerals inside that rock become unstable. And if you kick up the temperature and pressure a notch, some of those clays will become unstable and will transform to a stable cousin mineral, such as mica, muscovite, biotite, or chlorite. When that happens, these new mica crystals are very, very tiny. They're microscopic still. So this rock is going to have what we call a philitic texture. It's going to have a satiny, silk-like sheen to the surface in reflected light. It's still going to have the layers of slate, but slate is layered and kind of dull. Philites, or philitic textures, are layered but kind of shiny, but not like highly reflective. That happens more when we have a schistose texture in a metamorphic rock. In this case, those micas have started welding together with increased temperature and pressure, and now they're growing. And so these rocks are going to have a flaky, scaly appearance where you can see little flakes and scales of different types of micas. Now, we've gone from low-grade metamorphism with slates, and we've increased it then into philites, increased it more into schistose. And when we get to gneissic foliations, these are under such heat and such pressure that the rock almost melts. Any higher than this, and it probably is going to start melting. But even as it's not melted with a gneissic texture, the minerals do start behaving a little more plastic-like. So with a gneissic rock, or a gneiss, you're going to see alternating bands of the light-colored minerals and the dark-colored minerals in the rock. So they're kind of zebra-striped. You have black and white stripes throughout your gneissic rocks. And these are very, very high temperature, high pressure, high deformation metamorphic rocks. So if you were to start walking towards the Appalachian Mountains, as you got closer to the mountains, you'd start finding the rocks have a slaty appearance because they've been metamorphosed, but it's kind of low grade. As you get closer to the range, you're going to see philites, then you're going to see schists. And when you look in essentially the basic core of some of those old Appalachian mountains, you see lots and lots of gneisses, because that's when the heat and the pressure were at their extreme. So these are all foliated textures. If you see any of these, it's a foliated rock. They're layered. But we do have some that are non-foliated, which means they don't have layers, and that's because the rock that they started as, which we call the parent rock, didn't have any clay to turn to mica. So these end up just becoming very dense, and they have kind of a sugary appearance to them. So as you can see here, we have our foliated and our non-foliated rocks, and then some miscellaneous stuff. But we'll focus on the foliated and non-foliated for right now. With our foliated rocks, see we have gneiss, schist, phyllite, and slate. That's going from high to low-grade deformation. And then for our non-foliated rocks, because they don't have any clay to turn into mica in the first place, they don't get a bunch of layers in them. However, if the parent rock of a non-foliated rock is made of calcium carbonate, let's say it's the sedimentary rock limestone, when that metamorphoses, it's going to become marble. Or we could have the non-foliated sedimentary rock sandstone, quartz sandstone, and that becomes metamorphosed where the individual sand grains end up welding together and you end up with a quartzite. Now these two can look very similar. You have to run tests on them the same way you would minerals, because marble is going to be made of calcite, so it's going to react with acid to calcite. And quartzite is essentially welded quartz, so it's going to have similar properties to quartz. So you'll be looking at these 6 metamorphic rocks as well. So hopefully that gives you a little bit of a primer of what we'll be doing in lab. Again, if you need to rewatch this video before you come to lab, please feel free to. Definitely read the lab assignment in completion before you come to lab, and complete the pre-lab assignment on Canvas before you come to lab. My idea is that you'll come to lab, look at the specimens, take your notes, and then you can head home to finish the exercise and upload it remotely. This way we keep people moving through the lab at a pretty good pace while everybody can kind of take some space apart from everybody else. So you want to bring the Lab 1 printout, or better yet, bring your laptop with it downloaded to lab, and please, please, please be prepared to get started right away. By doing this video, I kind of just took up 30 minutes that I don't have to do now in lab, so everybody can get started much faster. What you're going to be doing is identifying about a dozen minerals. You'll be looking at about 6 igneous rocks and about 6 metamorphic rocks. When you've gone through identifying everything, you can then upload your completed lab to Canvas or email it to me. And next week I will have a new video and a new lab exercise set up for our sediments and sedimentary rock labs. If you have any questions, please feel free to let me know, and I look forward to meeting everybody formally in lab.